Welcome to today's Explainer, where we are taking your Cambridge Computer Science exam and completely flipping the script. We are treating your syllabus 9618 paper exactly like a high-stakes corporate boardroom pitch. Picture this. You're walking into a room full of executives to pitch a $1 million idea. You wouldn't just stand there, sweat profusely, and throw random, disconnected facts at them, hoping something magically sticks, right? Absolutely not. You justify every single point with hard data. You'd have a crystal clear strategy. You'd anticipate their toughest questions before they even open their mouths. Well, guess what? That is exactly how you need to approach your Cambridge exam. Today, we are going to master the control unit, or the CU. We are officially moving away from passive, robotic memorization and stepping into the role of a strategic, high-level expert. By the end of our time together today, you are going to see exactly how to structure your answers so that the examiner, who is essentially your board of directors, has absolutely no choice but to award you maximum marks.
Okay, let's dive right into this by addressing a massive question that genuinely plagues so many candidates right from the starting line. Why on earth do students find evaluating algorithm efficiency, particularly when it comes to the control unit's operations, so incredibly hard? To really understand this, we need to look at two typical students. We're going to call them Alex and Sam. Now, when Alex opens the paper and sees a question about the control unit, sheer panic sets in. Alex's strategy? Overload the answer with raw computer science facts. It's a complete, unfiltered brain dump of every single thing they've ever read in the textbook. They write paragraphs and paragraphs, but here's the catch. There is absolutely no analysis. None. Then you have Sam. Sam is watching the clock tick down, starts rushing frantically, and completely misses the specific command word requirements in the prompt. Sam might actually write a beautifully detailed answer, but it's for the completely wrong question. Because they didn't decode the command word, their answer is totally irrelevant. Both of these students lose massive, massive marks. And here's the tragedy. They don't fail because they lack knowledge. They fail because they lack a systematic answering strategy. They aren't pitching their answer to the board. They're just guessing and hoping for the best.
I want you to really absorb this direct quote from a senior examiner. It establishes the massive stakes we're dealing with and sets our exact mission for this session. The control unit's purpose and role is literally one of the most misunderstood areas in the entire computer science syllabus. Imagine examiners sitting there at their desks, staring at a mountain of past papers. They've got their red pens out, and they are watching student after student make the exact same tragic mistakes that Alex and Sam just made. Brain dumps, missed command words, no context. But today, right here, we are going to transform those red pen marks into massive green check marks. We are going to decode those command words once and for all, and we are going to build a protective framework that shields you from these common pitfalls. Let's fix this widespread misunderstanding right now and secure your top grade.
To pull off this transformation, here's our strategic briefing agenda for today. First, we'll cover the core principles. Second, we're going to build a foolproof procedural framework. Third, we'll dive into critical analysis to audit your algorithm quality. And finally, we'll cover examiner alerts to ensure you dodge those historical traps. Let's get straight to work.
We're kicking things off with Section 1, Core Principles. This is your foundational blueprint. You can't build a skyscraper on a swamp, and you can't ace the 9618 paper without this solid ground.
The theoretical architecture of the control unit requires absolute, razor-sharp precision in your definitions. You also need a deep understanding of causal relationships. You literally cannot afford to be vague here. Think of this as the highly technical specifications of your boardroom pitch. The control unit is the conductor of the CPU orchestra, right? It directs the flow of data, it decodes the instructions, and it manages the entire execution cycle. But listen to me carefully. Just knowing that basic definition isn't going to cut it for top marks. Top-performing candidates exhibit a connected conceptual understanding that is effortlessly transferable to completely unfamiliar exam contexts. You need to know exactly how a control signal, like one telling the arithmetic logic unit to add two numbers, actually cascades through the entire system, how it fetches the instruction via the program counter, holds it in the memory data register, and ultimately decodes it in the current instruction register. It is all about cause and effect during the fetch-execute cycle. If A happens, B is triggered, resulting in C. That's the level of precision the board is looking for.
Now, this is where it gets really exciting. Connecting the control unit to other areas of the syllabus is the absolute secret to top-tier performance. Examiners explicitly note year after year that candidates who make cross-topic connections achieve significantly higher marks. And this is exactly where we introduce our ultimate weapon, the PEAL framework. That stands for point, evidence, explanation, link. Top students don't just write sentences. They structure their computer science answers with military precision. They make a clear point about the control unit.
They provide concrete evidence pulled directly from the exam scenario. They explaining the technical mechanism in detail. And finally, they link it back to the broader system or a totally different syllabus concept. It's a game changer.
You must be fully prepared to demonstrate absolute mastery across these three distinct cognitive domains if you want to satisfy the exam's assessment objectives. And look, whether you are building your foundations in the IGCSE code 0417, 0478, 0983, 0984, or O-Level 2210, or you're tackling the advanced heavy-hitting requirements of the Cambridge 9618 syllabus, these cognitive domains remain perfectly constant. First up, knowledge and understanding. This is your baseline ability to recall the raw facts. Second, application. This is where you take those facts and specifically apply them to the unique scenario provided in your exam paper. And third, analysis, the absolute highest tier. This requires you to break down complex systems, evaluate different alternatives, and ruthlessly justify your reasoning. Remember Alex? Alex usually stops at knowledge, just drops facts and leaves. Sam completely messes up the application because of rushing. We are going to ensure you hit all three levels perfectly, focusing heavily on that analysis tier to absolutely maximize your mark potential. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE-ish to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, let's transition into Section 2, Procedural Framework. This is where we take the theory and turn it into a relentless step-by-step method.
The absolute most crucial takeaway here is executing this exact 5-step procedural framework to guarantee you capture every single method mark available. Let's bring Alex and Sam back into the room. If they use this blueprint, their answers would transform overnight. Step 1. Deconstruct the question. You have to literally attack the command word. Is the examiner asking you to describe, to evaluate, or to explain? Those require 3 completely different structures. Step 2. Extract relevant data straight from the scenario. Step 3. Select your analytical framework. This is where your PL structure shines. Step 4. Execute with clear notation, meticulously showing all you're working. And Step 5. Present with correct high-level terminology. Imagine sitting in the exam hall. You apply this framework and you watch your answer transform from a chaotic brain dump into a masterpiece. You are no longer guessing. You are systematically processing the question to extract maximum value. We call this the Computer Science Success Blueprint.
What's brilliant about this systematic processing is that it directly mirrors your practical programming skills. It creates this continuous, seamless loop of execution and evaluation. When you design algorithms or evaluate the efficiency of the control unit, you can't just write it and forget it. You must test your assumptions. You must evaluate the performance outcomes. It is a rigorous, cyclical process, and mastering it builds incredible exam day confidence. You become unstoppable. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
Welcome to Section 3, Critical Analysis. It is time to audit your algorithm quality. We are moving into the interactive workshop phase of this explainer, so get ready to participate. As a top-tier candidate, you must rigorously evaluate algorithm quality by identifying its time complexity, its space complexity, and its performance at boundary conditions. Okay, we're doing Challenge 1 right now, the data scan. I am mentally putting a 60-second visual countdown timer on the screen. Go! I want you to look at this data and extract the core trend. Scan the elements. What is the undeniable relationship here? Time's up. The core trend is that every single evaluation element directly and measurably impacts a specific aspect of system performance. Time complexity is not just some fancy buzzword you throw into an essay. It dictates exactly how fast the control unit can actually process instructions. Space complexity dictates your memory bottlenecks. Edge cases literally determine if the entire system crashes under unusual loads. When you make your pitch to the examiner, you must connect these specific elements directly to system performance to secure those top analysis marks.
To truly excel, you have to think like a seasoned executive. Top-scoring candidates act like boardroom executives by actively comparing alternative approaches and always justifying their decisions with concrete evidence. Time for Challenge 2, find the flaw. Listen to this sentence written by a student. Solution A is better because it is faster. What is the critical flaw there? Think about it. The flaw is that it completely lacks evidence and totally ignores any trade-offs. The examiner will give you exactly 0 marks for a baseless claim like that. Now let's jump to Challenge 3, speed writing. I'm putting 30 seconds on the clock. If you had to write a perfect Peel paragraph under pressure, it would sound exactly like this. Solution A significantly reduces time complexity, that's your point, as demonstrated by the fewer fetch-execute cycles required in the provided factory automation scenario, that's your evidence. This means the control unit can process the sensor instruction set far more efficiently, there's your explanation, ultimately leading to higher overall system throughput compared to Solution B, even acknowledging the slightly higher memory requirement, and boom, there's your Lincoln trade-off. That, my friends, is how you execute flawless critical analysis.
Moving into our final phase, Section 4, Examiner Alerts. We need to audit historical data so you can avoid the traps that have destroyed grades in the past.
Examiners explicitly and repeatedly warn against these 3 recurring errors that will instantly derail an otherwise perfectly solid exam pitch. First up, answers that are way too vague. If you write something like, "the CU controls things," you are getting 0 marks. 0. You need hyperspecific technical details. Second, forgetting to check boundary conditions and edge cases. If an algorithm is processing an array of data, what happens at the very first index? What happens at the absolute last index? The control unit has to manage those specific memory addresses. You cannot afford to ignore them. And third, perhaps the biggest, most devastating trap of all, answers that are not specific to the given context. If the exam prompt is about an embedded system inside a smart washing machine, your answer better be talking about water sensors and motor actuators, not a generic desktop PC keyboard. Context is everything.
Look at this stark contrast here. This perfectly illustrates the difference between a failing grade and an A star. The classic mistake is the Alex approach, providing generic, memorized textbook answers without any specific details. It's just a lazy brain dump. Top-scoring answers, on the other hand, act like a meticulously tailored boardroom pitch. They connect the deep theoretical concepts of the control unit directly to the exact context given in the question. Every single piece of data you present to the examiner must serve a strategic purpose and directly address the prompt. To achieve this consistently, you must rely on the 3 pillars of our answering system. Number 1, command word decoding. Number 2, strict application of the Peel framework. And number 3, using a time management matrix so you don't panic like Sam.
If you write this down, bold it, underline it, and highlight it. Always link every point to the given scenario. This is the ultimate, non-negotiable golden rule of the Cambridge Computer Science exams. Whether you are explaining the fetch-execute cycle, evaluating algorithm efficiency, or describing the control unit's architecture, if it doesn't link back to the scenario on the page, it does not count.
As we wrap up this explainer, I want to leave you with a massive, provocative question. When you walk into that exam hall, how are you going to act? Are you going to be like Alex and Sam, relying on generic memorization, panicking at the clock, and dumping irrelevant facts onto the page? Or are you going to walk in there like a high-level boardroom executive, ready to execute a precise, strategic, context-driven pitch that forces the examiner to give you maximum marks? The blueprint is fully in your hands now. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. Subscribe right now to @Ace the Exams IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.